zone for
So
diamond.
you're not sharing your screen yet.
It's not shared. Okay.
It's not shared.
Share now.
Okay, now it's shared. Yes, sir.
So for diamond lattice or FCC lattice, both have same Brillouin zone structure. Diamond lattice and the FCC lattice have same Brillouin zone structure. So I draw last day. I drew the diagram. You should check the structure by book because hand drawing should not be always perfect. The structure is something like this. This one. So you find hexagon and rectangle. This one, two, three. Maybe this is the center. I'm drawing. The center is here, gamma point. Center of the reciprocal lattice. This is gamma point 0 value. And this one, let's assume along the x direction. This is along x direction. This is along y direction. This is along z direction. From the center of this rectangle, z direction. You can also call it 1, 0, 0 plane. This is 0, 1, 0 plane. This is along 0, 0, 1 plane. This one is center. If I say this is the hexagonal center, so you can consider along this. But this one in general, now we call this is along this direction. This point is called L point. L point, the center of this hexagon. So maybe I will slightly skip the origin, then it could be better to draw. But okay, let's keep it. So you can find these types of L point. This direction we call delta direction. This direction, x, y, z, all call the delta direction. And this is the L point. This direction in general called the alpha direction. Alpha capital. And if you consider this point at the edge, in general called K point. This point is called K point. Now, few important things. Based on that, now I want to draw the energy band diagram. So earlier I give you the concept how to draw the band is origin, but we tentatively consider the schematic. I always said the schematic energy band diagram is something like this. And in the last class, I try to draw the band diagram of of silicon. This is we call the valence band. This is schematic and conduction band that we earlier drew. Now I want to remove and want to draw the actual Venn diagram based on this Brillouin zone structure. So let's this from center, this is gamma point. We consider this center is gamma point. Gamma point is the origin. So momentum value we consider is 0. Now the edge, this one at 2 pi by A is the first Brillouin zone. For FCC lattice, you know that A star reciprocal lattice structure is, we can define 2 pi by A, 2 pi B cross C divided by A cross B cross C. For FCC and FCC and diamond lattice, A, B, C are same. A equal to B equal to C. You can find 2 pi by A. So this is the 2 pi by A, and this is same as the momentum vector. You know, when I solve this reciprocal, this infinite boundary condition, you can find K, you can find n pi by A. You got it. Okay, K is the momentum. So this momentum and this reciprocal is almost the same unit, and this is the same as the momentum. So that's why we call the K direction. This is momentum direction. So K direction, if you move along this, it could be one of the direction you are moving K. Let's assume K X direction. So from this point, you are moving along this side Kx direction. So if you move along this direction, you can find the valence band at gamma point is something like this. Along 100 direction, you can find something like this. This is the movement along 100 plane, Kx direction, or along the delta direction. If you move along from this point to this L direction, this gamma, this alpha direction up to L point, center of the hexagon. If you move, this is the 1-1 direction actually, 1-1-1 plane. So if you move, you can find something like this. This is along 1-1 plane or gamma direction. So this is the set along 1-1-1. This is along 1-0-0. This is along alpha direction. So this is the valence band. This is the, you can find, this is the valence band. This is valence band. Now you can find another two part in the valence band direction. Here minus 2 pi a, you can consider 1 direction 2 pi a, if I say generally minus, but in here in this position L point, this is the L point. If I say L point along that, you can find along this L direction at 2 pi by a. So this is the valence band. You can find two band in valence band. Something like this. One is the lower band, this one, another is the upper band. Now I am to draw the conduction band part. Conduction band you can find, just drawing dotted. This one, just one. Could be somehow like this. Somehow. This one also, this one, it will come something like this. This part. Zoom in. Except sorry. Tentatively, you can find this diagram. Little low. To clear fully about this drawing. These types of diagram you can find where this is the conduction band. We have the other band here, but tentatively you can get these types of band, or it's a combination of two bands, so it's better to draw the single band. For your simplicity, I just want to draw one part, not combination of the other. Simply I want to show you something like this. It could be better for you. This should be little high. For simplicity, I keep it like this. Now, this K gamma equal to K point, you can see here conduction band is maxima. Conduction band is maxima here. So, and this value magnitude is around 3.4 electron. Now, if you measure from here, this is minima. Minima, conduction band minima should be your band gap. This is 1.12 electron. And this location, if you measure from this is location from here. If we measure from this side to this one, 0.84 into this x point 2 pi by a. And this direction as the L point, as I draw, this is L point at 1 direction. In L point, you can find another gap if you measure. This gap is 2 electron. Now you can see the what is the minimum gap. Minimum gap from the top of the valence band to the bottom of some minimum of the conduction band. This one, this is the lowest gap. This lowest gap of silicon is 1.12 electron. You have direct band gap at gamma equal to 0, but that value is quite high, 3.4 electron. At L point, you have the gap is 2 electron. So minimum gap between the conduction band and the valence band is 1.12 electron, and what we consider the silicon band gap is 1.12 electron, this one. So now you can consider that from the center, from this point, if we move along the x direction, you can find it's 100 plane, and you have your 100 is along this direction. Your minima is here, along minima is here. So your minima you will get at here, little inside around 0.84. If we consider from here to here is 1, so 0.84. So 0.84 into 2 pi a, 2 pi by a, you can find this minima. Now you know that the your 100 direction and 010 direction are same direction, only the change of the a coordinate. So same way you can find a minima here. Same way. So in 3D, if we consider this is along the x100 direction, so same phenomena you can find along the 010 direction. So I can write 0, 1, 0, you can get same result. So this is 1, 0, 0, 0, 1, 0, you can find same result. Same as 0, 0, 1 direction, 0, 0, 1, you can also get same band structure 0, 0, 1 direction. You can find this maxima minima variation. So x in, you can consider this x, y. Just consider this is x, this is y, this is z direction. So you can find minima here. If this is the edge of this gamma point here, this is the edge, this is the alpha point, alpha, this is alpha direction, this is also alpha direction. So you can find some minima here, here, and here. So similarly, you can get along 1 direction. So if this is, we consider this L point is 1 direction. So other point here, 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 you can get the other. This one is also 1 plane. You know, this one also 1 plane. So you can get this 2 point, this point here. So same, you can find the minimum 2 electrovolt at this region. So for 0, 0 direction, 1, 0, 0 direction, you can find that this, if I consider only this along this alpha direction, means x point, these are called the x point also. This point is called x point. These are x point. This x point, and along the alpha direction, you can find this three minima condition. Now you consider the same phenomena for this one. You can find opposite side x2 minus x. You can find another point plane, the opposite side. Same this one, if you construct opposite side, you can find y2, y prime plane, and z2 minus z direction, you can find plane. So you can find another three minima. Actually, you can get 6 minima due to this x point, 6 minima. So your conduction band minima is 6 for this x point, the band gap 1.12. This point, this have 6. This each point, this point we call the valley. We call the valley. These are valley point. So you have 6 equal valley. So you can find 6 valley, all have same energy at 1.12 electrovolt respect to the top of the maxima of the valence band. So these are called 6 valley. Valley. 6. Then you add the plural part valleys, but I just want to consider this valley. This 6 valley is exist here. And now if you only exactly move along 1, 0, 0, 0, 0, 1 or 1, 0, 0, 1, 0 direction. So this direction, in general, we notify the opposite plane. This opposite plane, we call, if this is 0, 0, 1, 0, 0, the inverse plane means negative side, we call 1, 0, 0 inverse. This is 0, 1, 0 direction. So the negative side is 0, 1 in inverse 0 direction. This is 0, 0, 1 direction. Then this one is 0, 0, 1 inverse. So this six direction, 6 plane you can find, and this each valley you have the 6 valley. So this 6 valley can exist exactly this point. Now this is exactly along the your kx, ky, kz direction, you can find this point. Now if you want to slightly modify your position in kx to ky direction, kx to kz direction, then this value slightly modify. So you can find, if you modify in 3 directional case, if you define this point now in 3 directional place, it should not be exactly along this 0.84. It tried to modify this position 0.84 and it slightly it have the equi-energy. If I draw this line, so it should be something like a rugby ball. Exactly 0.84 position, that is due to only, this is due to the along the 1000010, exactly along the kx ky kz direction. But if it try to define, it may plus minus 0.84, and in this all the rugby ball surface is called the equi-energy surface. Equi-energy surface. This is equi-energy surface. So all direction, this six valleys should have this rugby ball surface is a ellipsoidal surface you can find. Equal energy, and the position, this x position will slightly varied, and you can get the rugby ball all have same energy, but k value is slightly different for each. This minima position is different for each of this valley direction. You will get this 6 valley condition. This is for silicon. So in reality, this is one directional we consider, means kx and this L direction. You can find these types of diagram. If only consider this 6 minima valley, this valley for 6 direction means kx, ky, kz, and their inverse direction means negative side. You can find this 6 valley. So this valley we may note it by MC. I note it by MC valley. So this valley, number of valley is 6 for silicon. For germanium, this valley number is 4. And for gallium arsenide, I will draw the other structure. For gallium arsenide, if I want to draw this diagram, you can find in gallium arsenide the structure should be something like this. Same gamma point. This is the gamma point. This is along delta. This is delta point is that point. Along the direction is delta. This is along, we call this is along, this is alpha direction. This 10111 plane. This is 100 plane, means including all come 6 direction. So this is k point, I mean x point. This is your, or this point we call the L point. So you can find same, of course this splitting should be 2 slide like this. And you can find slightly, and so on. So you can see this is your valence band, this is your conduction band, and you can see the minimum is here at the center of the Brillouin zone. Means you can find along k equal to 0 gamma point. The minima is the top of your valence band, no k difference, and this gap is 1.14 electron. Since no k difference is there in the minima of the conduction band, this is called direct band gap semiconductor. And here you have the minima here. This gap is from top of this 1.99, around 1.9 electron. And here your minima is far away from, you have k value different, the momentum difference, so momentum vector. So This difference is there. So we call it indirect band gap semiconductor. Indirect band gap material. This is silicon structure. So now I hope you get the idea of two types of semiconductor. One is have this types of K value, the minima of the band gap, top of the valence band and the bottom of the conduction band, and have no change in the momentum value, K value, or in case of the other case where you can find a change in the momentum vector. So this difference if exists, then those part we call the indirect band gap, and for those part where no gap is there, no K value is required, then we call it the direct band gap semiconductor. So these two types case you can find, but one part I still not explain this lower part why we have the two bottom value. Okay, this the valence band you have two band structure. What does it signify? Here you have the other value top part, you can find other types of get so on. This way you can find this is the other excited level. This is the ground level, the other band is the above of that. You can find other structure, but for you the lowest is sufficient. But the bottom you can find two other things. So how we can identify this plane? So we know that E equal to h cut square by 2. Am I right? We solve energy, it depends on the momentum, and that I partially solve all these types of problem, one-dimensional potential well. I explain you what does this mean. Energy is Ek is depend on h cut square by 12. So it's momentum dependent. Okay. So now you can do this dk equal to h cut square k by m, and d2 ek2 is h cut square by m. This m equal to h cut square by d2 ek 2. You can consider this m, this mass. This mass is not the normal mass. This mass now depend on this ek and k movement. So here you can find this is the energy scale. Here we plot this top, this axis is energy. Same as here. This is energy axis, and along this is the k axis. So this is defined that the changes of your this the energy with k. So this second derivative, the slope d2 ek dk2 is the h cut square divided by this one is a mass, but it's depend on energy and energy. So along the k value. So that's why this types of mass is not exactly your particle mass or free electron mass. This mass is called the effective mass. Effective mass. So mass, if you are in a medium where energy will different, you have the different values with respect to the momentum direction you are changing. If there is a different value, which way you are moving along the energy, or the change of the energy with respect to your direction, if such happen, then you can find the mass. This mass is called the effective mass. So electron moving from one part, if electron moving from here to here, you have different mass, and since this slope is different, electron moving here to here is different. So this mass is called the collective mass or effective mass of those particles. So this mass is now can be defined as in a medium or in a solid. If a particle solid, if in the medium, if some electron is moving, then or the any other types of particle moving, their mass will depend on the energy value or the energy, the change of the energy. So this mass is called the effective mass. Is it clear? Now the question is, this mass can be positive or negative? Can you say? Do you have any idea that from here, just from this mathematical relation, can you predict the mass should be positive or negative? No one can predict the idea of the mass? I didn't get any response from you.
Can be positive or negative.
Sorry, can you be little louder?
Then I'm saying that it can be positive or negative because of that denominator term.
Yes. So if the slope d2 dk2, if the slope is positive, then your mass is positive. If the slope is negative, then your mass is negative. So two types of mass, that this mass, effective mass, can be positive, can be positive, can be negative, depending on the slope. If I move to this diagram, you can find that this slope, some part, most of these cases from here, the minima, if you move along this slope is positive. From this point to this one, the slope is positive. So this slope, the particle present in the conduction band, that is the electron, presence of electron in the conduction band. So this mass is positive mass. Electron mass is positive mass. If now you can see here, the slope always be negative slope. This slope is negative slope, and the mass which electron, absence of electron, that's I explained earlier in the valence band, is the positive charge. So it called the hole. So hole mass is negative. Now this slope can define the mass of the hole, the negative mass of the hole. If I say hole, this whole mass can have two types of mass it can exist. One is light mass, low mass, depending on the slope value. One is the higher slope, another have the lower slope. So based on that, we call this light hole. This we call light hole or heavy hole. These two types of hole. One is the light hole, another is the heavy hole. If this is the formula H2 D2 dk2, the slope, depending on the slope value, one should be light hole, another should be heavy hole. So it is inversely proportional to the slope. So can you say which one is the slope for light hole and which one? You have the two slope of this two band. So which one is the light hole and which one for the heavy hole? Can you predict from here? So this slope is smaller slope. This is the high slope. So that means 1 over this is your or the effective mass. So this is for light hole and this one for heavy hole. So these two slope I draw for the two types of holes. One is for the light hole, another for the heavy hole. So two types of hole exist in the material. One have the light mass, another have the heavy mass. So these types of hole present in the material. So overall, now you can get the idea that the material can have the conduction band, and you can identify that due to this presence you have the minima value for silicon is 6 value. In case of the germanium, we consider the structure should be little minima should be along here, along this. and it is tentatively 8 site, but half of this considered as the value. So 8 value will, say 4 value will be there for or case of germanium, and it could vary material to material. If you want to try to study the material, you have to calculate the structure and identify the material. So in other types of, there are several point of view you can find, but each material it could have different. But at this moment, you don't need to go on detail. For graphene, I draw earlier, you have the 6 minima value exist in graphene. Yes, 6 minima value exist also in graphene. So those are the other point there are you can find in details later on in the higher level of study. You can identify those things. You can able to calculate this diagram by tight binding approximation model or density functional theory. You can use for small structure, you can use density functional theory, or for I just give you the term, I don't want to go in detail. For the for solid bulk structure, you can use the other types of exact model, except with some approximation, tight binding model. If you want to use tight binding model, you can get the structure tight binding model. Using this, we can get the structure using the this whole types of interaction. You can consider the potential due to this interaction of the electron and the nucleus. You could take this all potential for n number of particle, then you can find this types of structure, exact structure you can find, and then you can get the idea that where minima is. So I took this diagram based on those models, and you can calculate this part for different materials. This will change, and you can play with this material. So this important thing I just want to mention, this 6 value, or for gallium arsenide, if you consider this is you have no value in the for the conduction band minima, you don't have value. It's a single value state, so you don't find this value. So it should be a sphere in the center along the gamma point. So you don't find this value. So for gallium arsenide, you don't have values. This same conduction band minima is single value. For the other type silicon, you have 6 value. For the germanium, you have 4 value, and so this 4 value, that means if you want to move along the x direction, y direction, any direction, you can reach this 6 value of the minima. In normal bulk classes, all have same energy, but if you have any problem in one of the axis in your 3D material, if you have some strain stress, then this value 1.12 electron on the conduction band, it may change. It may this value or this minima value may change, and then you have the noise. You have the problem in this energy. So those value is important. It may some perturbation may happen whenever you apply something external problem to the material. So if you want to, if you somehow you want to, as I say, confine of one of the direction, then that value, these two values. Let's assume along the z direction, you change the confinement. As I said, the two-dimensional material. You want to create two-dimensional material. So x, y remain same energy, but z direction will modify. So your value position will change this energy. So you can remove this 6 value into 1. You can have 4 into 2. 4 have same energy, 2 should have same energy. So it should have modified your value, and then it will split into 2 energy. One should be low. Of course, this 4 should be lower value energetically. This remaining x, y should be lower, and the z direction, or if we confine it in the z direction, then it will change its in energy. So it could be discretized along the z direction, and this should be higher value than this value, than the 1.1. Is it clear? If we have any queries here, I want to take now. After that, I will more to change some. I want to calculate the DOS value, density of state of this material. If you have any queries, please let me know. Have you understood? Or you have any queries, or you did not understand anything? If you want some part I have to repeat, please let me know, then I'll repeat those part. This is very important concept and you have to understand. No queries? Okay. So now I want to calculate the density of state. To do so, you know that we have calculated earlier that Ek equal to h cat square by 2m. Now this is become, earlier we wrote it as m. Now I want to change it. Since it's m, this mass is depend on the direction. So it should be the effective mass h cat square by 2m star. In three-dimensional case, the energy is something like this. But k square equal to this one. Okay? This one. Ek energy is k dependent. Now, if in 3D, if I want to draw some structure xy, this is kx, ky, kz. So I want to in 3D, you consider a football. Consider football. So you have, I just one corner, I just open. Let's assume the football, you have this one full. So I open something. So football have some thickness. So this one in K I know, and this cell thickness is dk. So this thickness is dk. So this is football. Now I want to calculate that how many k value this dk region in cell of this the thickness, this dk thickness in three-dimensional football structure. If you consider how many k state is there, so this is defined by dk, k number of state present in this per unit decay. So in decay thickness is this one. How to calculate this one? To do so, we generally this one define per unit reciprocal. This ek value is in the reciprocal lattice plane. We know that k is the in the reciprocal lattice plane. So in the I considered in this x y the kx ky kz in the reciprocal lattice plane, same as it could be difficult to reach there. So here I consider this structure. Let's assume simplifying this Brillouin zone in a such simple sphere. We just simplify this model to a simple sphere. So now we want to get the per unit. This is the total number of case. This is defined per unit reciprocal lattice volume. The k value present per unit energy per unit k value. This dk value is the number of k value per unit reciprocal lattice volume. This is the meaning of decay. So now you want to how much the the volume of this part. 4 pi, you know the surface value is 4 pi k square into dk. Am I right? The volume of this cell 4 pi k square into dk. So volume of this cell, if it's a sphere, so area is this one. 4 pi, surface area is 4 pi k square into thickness is dk. So 4 pi k square dk. This is the volume of this k part, and the reciprocal lattice volume, total reciprocal lattice volume is 8 pi cube by v. You know that 2 pi by a into 2 pi by a into 2 pi by a. This is the reciprocal lattice volume. So 8 pi cube divided by a cube. So v volume. This is the definition of your decay. Now, if we do the analysis, simple v square remain, 4 become 2, k square dk by 4 pi square. So this dk is now this one, where v is the real lattice volume. V is the real lattice volume. Now, this I want to change this k value now in terms of energy. So unit energy, how many state available per or k point, how many energy level available per unit energy. So this is should be dkd. So now I have to convert the relation in terms of energy, where we know that E equal to h cut square k square by 2m. So we can write dE equal to h cut square k dk by, I want to keep 2 by 2m. Now we replace all this value here. 2k dk you can cut here, but I need the relation. So d h k dk you have to replace v. K dk means 2m by h cut square de, not 2m, so it's m, now become m by h cut square de. So this gone. So h cut k dk value is m by h cut de. Now you remain 1k. K is root over 2me by h cut square. So you put the other v by 4 pi square into root over so this is your density of state per unit energy per each energy. This is called density of state. Each at energy, how many energy level available? That is called density of states. If we consider V is unity 1, V is unity, real lattice dimension is 1, let's 1 centimeter cube. So then V is 1. So it should be 1 over, I am taking 4 pi square by 1 to take 1, 2 here. So we can write 2 here. So it should be 2m. So I want to write 2m by h cut square whole to the power 3 by 2 into e to the power half into dE. So here you can find the density of state d equal to 1 over 8 pi square 2m by h squared square whole to the power 3 by 2 e to the power half d. This one we consider for k value. We know that each k value have accommodated 2 electron due to spin degeneracy. See, so you have to multiply by this 2 value due to spin degeneracy. 2 for spin degeneracy 2. I add 2 here. So your total number of state is 1 over 4 pi square 2m by h square whole to the power 3 by 2 per unit volume is real lattice volume dE. Now this is k along each k direction. You know that you have the 6 value. So you have to multiply by this value number. MC is the number of valley minima, conduction band valley minima. So this is your density of states. So we can write the density of state is dE dk is mc by 4 pi square 2m by h square whole to the power 3 by 2 e to the power half d. This constant you can consider in somehow. I'm just consider one constant. So in C, if we assume here, or any constant I term is, I later define the another constant. Let's assume a constant into e to the power half into dE. Constant e to the power half dE. So your 3-dimensional case, density of state for 3-dimensional case, this is we consider for 3-dimensional case because the bulk value 3D means bulk material. For bulk material, now the density of state is proportional to e to the power half, constant e to the power half. If we plot dE, density of state, respect to E, you can find this should vary something like this. This is the proportionality of e to the power half. Constant, this is your energy. If you change the energy, number of state, electronic energy level is now vary something like this. This is your conduction band. You can find that the energy level for or state available for the particle is something like this. Do you have any queries? Simple. I may give you this calculation. So if you have any problem, please let me know. Again, I want to explain this one. We started from the 3-dimensional reciprocal lattice with the energy value Ek is h square by 2m k square, right? K square is kx square ky square plus z square. Then we consider the cell of reciprocal lattice. Then we consider the k point, number of k point available per unit reciprocal lattice. That is the definition of the k points density of state, you can say. So now we convert from this part to the energy density of state, number of state available per unit energy per unit volume of your this material. So this part now you can get, ultimately we get this is the MC is the maxima of number of valley maxima, conduction valley maxima by 4 pi square into 2m by h square whole to the power 3 by 2 e to the power half into d. D is both sides, so this is your the dE value. This part, this capital D, the density of state is this point. That means some constant you can calculate. This m is now not this m. This is effective mass. So I should multiply this one effective mass for all cases. Is it effective mass? This is effective mass. All m is now effective mass. And we are calculating this effective mass for conduction band or the density of state calculation. This effective mass m star M star, this the for density of state effective mass. If we notate this one or denote it by M star dE, so this M star dE, it's generally called, it's defined at the combination of your or the three different effective mass. So you know that as I calculate, if you add this part, what does is my effective mass is the variation of your or the state, which direction you moving, based on that your mass should be. So one part you are moving along from the center of the Brillouin zone to this direction. So this is your, it's called ML effective mass, the longitudinal effective mass. This ML star called longitudinal effective mass. It's both longitudinal effective mass. And I should make it thinner. And if you move along the perpendicular direction, perpendicular y and other, if you want to move along this longitudinal other two direction, if you get, then the other mass will come as a transverse mass, effective mass. This is called transverse. What happened? Effective mass. This is called MT star, transverse effective mass. So you can see this valley, you know, if you move along this valley, so this is longitudinal trace, and you can move along perpendicular valley. So these are the transverse direction. So transverse direction, you can see this thinner, I draw it. These are thicker, so mass is quite high along this. You have to, this is the rugby ball, along the longest direction. This is the longitudinal mass. The other two direction is the smaller mass. These are called the transverse mass. So if you want to calculate this density of state effective mass, if you want to calculate this density of state effective mass here, if you want to, this value, this effective mass should be the combination of these three mass. So mx star, my star, mz star. This is called with 1/3. We get this way, the combination can be taken by this way for density of state calculation. So this is now longitudinal mass ml star, and transverse is both same. So T star square whole to the power 1/3. So this mass we can replace here, and this is the, for density of state calculation we use this mass dE. So if density of state effective mass we have to calculate for silicon ml star. This ml star longitudinal effective mass value is as I recall, longitudinal mass is 0.98 into electronic mass. This M is free electron mass. How much the value of free electron mass? Do you have any idea? Nine. What is the order of magnitude of the free electron mass? 9.1 10 to the power minus 31 kg.
10 raised to power minus 31.
This is the free electron mass. So the effective mass, longitudinal mass is 0.9 for silicon. This is for silicon. Other material is so different. Gallium arsenide, it is higher than free electron mass, 1 point something. So this for silicon, this value is 0.98 free electron mass Me, and for MT is 0.19 into free electron mass for this one. So you can get this MD value. So this is the case where we can get the longitudinal mass or we can get the density of states of the bulk silicon. For bulk silicon, if you want to get MC values would be the value is 6, and you can consider this value, and the 4 pi square h card h is your h card is h by 2 pi, where h is the Planck constant. Planck's constant. So you know this value. So you can calculate the density of state variation with energy by this formula. Is it clear? This is very important thing. So some homework. Let's same way try to calculate the density of state for 2D material. I'll give you the example how to calculate this one. To calculate the decay value, you have to consider a thin disk, means ring type structure. From here you can consider K, and this is decay. So you have to calculate first decay value. That should be area. So you have to calculate this area first. Then this area divided by the area unit per unit reciprocal lattice area, that is 4 pi square by this area is different. So if I note it AK by the real area, A square means A. Reality is A into A. So based on that, you convert it to D. Question. This is your first homework. Second homework is for linear chain. So this is the origin you consider, and this distance you consider K, and this one is decay. So calculate this DE for this same way, giving some hints. Decay equal to here K. This is decay, length is decay only, divided by 2 pi by length per unit. This is the calculation. So from here calculate these two values. This is your homework. These two problems, you do calculate that how much the density of state, how density of state can vary. In case of 2D material, this is one-dimensional material. Same way you have to calculate, just convert this K value by EK value, by energy value. Then you can find these two parts. So this is homework. Have you noted it?
Yes, sir.
Okay. So now the next topic. Now you can get the
Excuse me, sir.
Yes.
Sir, for how long will the class continue? Because in about 5 to 10 minutes, I actually have to go somewhere.
2-hour class, as discussed earlier.
Oh, okay.
So this is the homework part. Now I want to discuss. If you don't find means it's difficult to capture at this moment, then I'll stop. Otherwise, I'll discuss. I'll continue the class for another half an hour. So now you have to understand few important points. This is the valence band, reality,
Sir, can we continue some other day the class?
Other day still you are missing several classes, okay? So
Sir,
we are
because
lacking behind.
so because you have already taught so many things, and I think we will like to have some time to grasp it. So
All want to do consider to stop the
Yes, sir.
all of you.
Yes, sir. Yes, sir.
Okay, let's stop here. Do continue. Do try to follow this class first. Then I'll add up some more thing in this direction. Okay.
Sure, sir. Thank you.
Okay. So let's stop here. Have a nice day. But try to read the all these topics. Then only you can understand the next class. If you miss here, then it could be very difficult to continue this class. All students should try to understand this up to this part. Then I will expand the class based on this topic.